binomial distribution? Binomial distribution is very common. It's the most common discrete distribution that we have in probabilities, and it was discovered by Bernoulli, and that's why we also call it Bernoulli trials. When we refer to Bernoulli trials, basically we refer to binomial distribution. When we work with a distribution, any kind of distribution, the first thing that we want to make sure is that we ensure that the distribution that we are working with is the distribution that we expect it to be. So the first thing that we want to make sure is that review and ensure that the requirements hold. For the binomial experiments, for any kind of binomial experiments, we want specific requirements to hold, and these are the following. First of all, that we have trials that they are independent of each other, meaning the probability for each one of the trials is equal, it stays the same, it doesn't change, and it is not affected by the previous trial. Also, that there are two possible outcomes and only two for each one of each trial, of the trials. We have one of the outcomes, we consider it to be a success. It doesn't really matter what it is. And the other outcome, we consider it to be a failure. The probability for success and consequently for failure is the same for each one of each trial. Also, the random variable counts the number of the successful trials. So the first three are the requirements that we set in order to ensure that the distribution that we are working with, the experiment that we are working with, follows the binomial distribution. The notation that we use is N is the number of trials, P is the probability for success, Q is 1 minus P, that is the probability for failure, and X is the random variable. Let's see an example. A certain surgical procedure has 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So in this case, we have success, we consider to be the surgical procedure and where it is completed and the patient doesn't die. And the probability for this is 85%. So this is our P. P is 85% or 0.85. So if we run an experiment for the specific one, let's assume that there are 8 surgeries. Each one of these surgeries is independent of the other. Now, in real life, very few situations we have where one trial is independent of the other, and we always need to ensure that we check this in real life situations when we do modeling. For example, if these 8 surgeries happen at the same day, I'm sure that the probability for the first to be a success and for the last to be a success is not going to be the same. So in this case, it is not a binomial experiment, and different factors need to be considered when you solve this type of problem. But for the sake of simplicity, let's assume that they are the same. Okay, so you have 8 surgeries. So the N in this case is 8 because your trials are 8. The probability for success is 0.85 for each one of the trials. Assume now that you want to find specific, if you want to look at the distribution, you have anywhere from 0 to 8. These are the number of surgeries that the surgeon can do. The probability is 0.85, the N is equal to 8, and the probability for failure is 0.50. So this is what describes your experiment. And then you can calculate the probability for all the different values of the random variable. So for example, if you have the specific problem that you have right here, you may want to calculate for N equals to 8 surgeries, and for P equals to 0.85. and for Q equals to 0.15. You may want to calculate the probability for specifically 3 surgeries to be successful in a day for the specific doctor. Since this is a binomial experiment, what you are looking for is the probability for this value of the random variable. The formula that we are using in order to calculate that is n choose r times p to the r times q to the n minus r. That's the formula. Where n choose r is 8 choose 3 times 0.85 to the third times 2, that is 0.15 to the fifth. So if you calculate this will be the probability that the doctor in one day has exactly 3 surgeries that they are successful. A different problem. A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. What we want to see, I guess, is if the probability is a binomial experiment. Is this a binomial experiment? And if it's not, why? What do you think?
It's not binomial because there's no replacement.
You don't have replacement, and if you don't have replacement, what's the problem?
Probabilities change.
Very good. The one trial affects the other. If you have a non-replacement, then you don't have independent trials. The trials are not independent. And when they are not independent, then the probability at every trial changes. Is there another problem here? There is a small problem. You have 3 different colors. By having 3 different colors, then this means that you have 3 different probabilities. You don't have 2 outcomes, you have 3 outcomes. You have either red, blue, or green. So you don't have success and failure. You have 3 different cases. So if any of the requirement fails, the experiment is non-binomial. This is the formula that I just gave you. N choose X, where X is the number of the specific value of the random variable, times P, where this is the probability of success, to the X, times Q to the N minus X. So here we are changing a little bit the probability. The probability is 75% chance of success on patients with degenerative needs. Find the probability of the surgery to be successful in exactly 2 patients. Okay, we did this example before for the different type of probabilities that we had. Let me go back here. We don't need to redo it. But what I want you to see here, now that you have seen the formula, is that, okay, it's not that difficult to calculate this. This is fine. The problem comes when we don't really care if the doctor has 3 surgeries. Who cares? Even the doctor himself doesn't care if he has exactly 3 surgeries. What he cares about is to have at least 3 surgeries or at least 5 surgeries. So in some cases, when we calculate binomial probabilities, we care about at least. In some cases, we care about at most. Suppose now that we want to find the probability that we have x to be at least 3. If we want the x to be at least 3, then we want the x to be greater than 3. So the probability that the x is greater or equal to 3 is equal to the probability that the x is equal to 8, 7, 6, 5, or 4. So we don't want the probability to be equal to 2, 1, or 0. So the probability for the x to be greater or equal to 3 is 1, the entire probability, minus the probability that the x is 0, minus the probability that the x is 1, minus the probability that the x is 2. Okay. So in order to calculate that, this is going to be 8 choose 0 times 0.85 to the 0 times 0.15 to the 8. So it's going to be 1 minus this minus 8 choose 1 times 0.85 to the 0 to 1, I'm sorry, times 0.15 to the 7 minus 8 choose 2 times 0.85 to the second times 0.15 to the sixth. So when you calculate binomial probabilities, in most of the cases, what you want to calculate is not just one of the probabilities, but several of them, because you will be interested either for a case where you have at least, like this one, or in a case where you have at most. For example, maybe the doctor focuses now on his failures and he wants to have at most one surgery that fails. So in this case, your P will be the Q and the Q will be the key, the P. And the probability to have at most one failure, it will be the probability that your X is less or equal to 1. So you would have to add the probability that you have 0 surgeries that fail plus the probability to have 1 surgery that fails. Calculating probabilities for the binomial distribution can get really long and tedious, but we have Excel and we have R, and we can easily calculate it, or you can write a very small problem, and this would be a great practice for you to write a program and actually it is on session 5. I think it's the second example that refers to that, on how to calculate probabilities for at least this many. So the probability, the binomial probability for X greater or equal to R or less or equal to R, and how to calculate that in Python. So we can discuss that if you have time, of course, this week in the Python discussion, and how to create a program that can help us calculate this without having to spend time to doing this manually. Draw a tree diagram, a user multiplication of this, and how to find the probabilities. I skip that because I'm sure that you can do it yourselves. Let's just review this. This is something that you're interested in. The formulas that give you the mean, then the variance, and the standard deviation for binomial distribution. In general, when you have binomial distribution, it's very easy to find the mean, the variance, and the standard deviation. And these are the formulas where N is the number of trials, P is the number of the probability of success, and Q is the probability of failure. So you just need to use those formulas. You don't need to look into the experiment. If it is a binomial distribution, then for sure these formulas hold. The rest of them, we don't need to do them together. I know you can do them alone. What I want us to review is the Poisson distribution. The Poisson distribution is similar to the binomial distribution. It is a discrete distribution as well. The difference is that in the case of Poisson distribution, we are counting the occurrences of an event in a specific interval. This interval, it may be a distance interval. So let's say how many accidents can happen in one day from here, from where I live to downtown Chicago. Or it can be a time interval. So how many accidents happened in a specific intersection at the span of 1 week. The experiment consists of counting the number of times that the event happens and occurs in a given interval. And the interval can be any kind of interval, as I said. The probability of the event occurring is the same for each interval. And again, we have a failure and a success. The formula to calculate the Poisson distribution is mu, where the mu is the mean for the specific distribution, to the x, where the x is the value for the random variable, times e, where e is the natural logarithm, to the negative mu divided by x factorial. Let's see an example. The mean number of accidents per month at a certain intersection is 3. What is the probability that in any given month 4 accidents will occur at this intersection? So if you know the mean for the distribution, then you can calculate the probability for any value of the random variable, no matter what it is. Of course, as you can understand, when the denominator becomes big, very big, and it falls far away from the mean, here the mean is 3. So if I make the denominator, let's say 100, then the probability will drop extremely, meaning it's going to drop to the 20th decimal digit, and it will show that it's almost 0. Still, though, in the Poisson distribution, the beauty that we have is that the probability doesn't necessarily is 0. It typically is 0. In the real life, we can consider it to be 0, but it can never be 0 for sure. While in the binomial distribution, since we have specific numbers that can happen, specific numbers that are possible values for the random variable, we can have probability that is equal to 0. We don't have intervals in time. We don't have intervals in distance. We have specific trials that repeat themselves.